a few people present and then a lot of people online. That's great to see. I'm very pleased to introduce Erin Thomas today as our Climate People Environment Program seminar series gets kicked off again. Erin got her bachelor's in meteorology from Penn State, and despite that, we still allowed her to come here and come to grad school here at University of Wisconsin. We're thrilled to have her here at University of Wisconsin, where she worked to get her PhD in 2017. And she worked on tropical ocean atmosphere interactions. Her PhD was on ENSO initiation mechanisms, so phenomena that influence the development and initiation of El Nino. From there, she had an opportunity to go to a postdoc in Norway to help develop a coupled model for polar prediction. And so this is in line with Erin's diverse set of interests and her work ethic as well. When we were talking about that, I thought, that's going to be a lot of work, and I think she was pretty excited about that opportunity. We're going to see some of the fruits of that labor here today. So she did a postdoc with the Norwegian Meteorological Institute, where she's continued to be and she's now a researcher at the Norwegian Meteorological Institute in Norway. And we'll hear about some of the work she's doing there. And recent news, she was just hired at DOE, at Lawrence Livermore National Laboratories.
Los Alamos.
Oh, Los Alamos, that's right. That's Lawrence Livermore yeah, okay, that explains. Los Alamos National Laboratories, which is a much better location than Lawrence Livermore, to help develop their help couple their sea ice, wave, and turbulence modules in E3SM, I believe. Yeah. Which, once again, is a tall order, but I'm confident that she's going to do awesome there, just like she has with all the other stuff she's done. So I'm super excited. I didn't mention she got her PhD with me in 2017, and so this is one of the other reasons why I'm just super excited to see what she's been up to. And just welcome Erin Thomas.
Thanks, Dan. Thanks for that great introduction. Yeah, as Dan mentioned, I've been here in Norway for almost 4 years now after I finished my PhD. I started as a postdoc and then continued on as a research scientist, all to work on the development of a coupled Arctic numerical weather prediction system. And so most of the work that I'll be presenting today has been done associated with the Nansen Legacy Project. It's a very large national project, and my component is a very small part of it, but I'm excited to share it all with you. And so just a really quick outline. We'll do a little bit of background, talk about why we're developing a fully coupled forecast system. Specifically, I'm going to focus today on the atmosphere wave coupling. That's been most of the development to date. Present some of the results from this model, as well as talk about a lot of the future efforts, which is really quite exciting work. And so at the Meteorological Institute, unlike a pure academic institution, the end goal is really to provide reliable and accurate forecasts for the end users. And so all of our research is really done with the end user in mind. And so again, ultimately the purpose is so the end user can make decisions, primarily in the Arctic is my research, to protect life and property. And so we are trying to improve our forecast quality in order to provide reliable and accurate information for end user decision processes, particularly in extreme locations like the Arctic. However, there's a whole lot of challenges that are very unique to forecasting weather in the Arctic. I'm going to outline just a few here, and then go into detail on why some of the coupled work that I've been working on can maybe help alleviate some of these problems that we run into. First and foremost is the availability and the quality of observations in a region that we're dealing with. On the right side of the screen here, you can see the domain that we're working with. The domain of interest for my work is outlined in blue. And so Svalbard is really in the center here, and then Northern Norway as well. And some of our observation sites are the little colored diamonds. I'll explain what those mean in a second. But you can see that really the observation network is very sparse. Ocean covers a very large part of this region. And so we are very challenged by the availability or lack thereof of these observations. The use of any observations that do exist is even further challenged by complicated surfaces, such as snow and ice coverage. Additionally, all of the models that we use have quite large uncertainties in these physical processes at the high latitudes. And so capturing complex interactions, particularly when it comes to ice, wave, atmosphere interactions that I'll be going into details on later, we have quite large uncertainties. And so this creates errors and biases in our forecast. And then lastly, there are a lot of small scale processes going on in the Arctic that are particularly relevant for our forecast accuracy. Things like polar lows happen at a smaller scale than a big low pressure system at lower latitudes, and these can be really challenging to accurately predict. And so on the figure, the colored diamonds are representing the root mean square error of sea level pressure forecasts. And you can see green is low error, red is higher errors, and there's a very clearly linear relationship almost as you move further north, the errors start increasing drastically. And so within the domain that I'm really interested in, you can see that these errors are in fact the largest for our area of interest for Norway.
Oh.
And so there are tons.
Hey, Erin, we got a question from John Martin. Hang on one second.
Sure.
Yeah, Erin, you're probably going to tell us later on, but it's nice to see you. What about 950 millibar vorticity? Do those forecast errors still have that distribution if you use something like that? Because you can just have, you know, a large scale dead low that's just way too low, and that can systematically makes your pressures too low at Svalbard. Is that
good question? I have no idea what our upper level skills look like. Everything I'm interested in, as this slide shows, is happening down at the surface. Fantastic question, and I really have no idea.
Okay, thanks.
Sorry. Yeah. So as I was saying, there are tons of processes going on in our forecast model, but my focus is really to improve what is going on way down at the surface. And so I'm very interested in how the ocean surface, waves, ice, and the atmospheric surface all interact. And so my goal is, again, to develop a fairly high resolution, we're talking kilometer scale resolution here, coupled atmosphere, wave, sea ice forecasting system. And so as I was just saying, there are many severe Arctic weather phenomena in the high latitudes that we're dealing with here that are highly dependent on these interactions at the surface. In particular, these forecasts are severely dependent upon heat and momentum exchange at the ocean surface. And so because of these severe weather events being so dependent upon the interactions at the surface, there's really a high demand for forecasts that capture these rapidly changing environmental conditions with high winds, big waves, rapidly changing sea ice conditions. So some of these severe weather events that we really want to nail in our forecasts are things like cold air outbreaks, polar lows, as I mentioned earlier. Those are a big one, as well as what's going on around the marginal ice zone. So interactions between the waves and the sea ice, motion of the ice, and things of that nature. And so again, I've been working for several years to develop a forecasting system that improves our short range forecasts by better representing these atmosphere, wave, and ice interactions. So we've got several challenges. And again, we're focusing on a few situations that we'd really like to get correct. So one of the challenges that we'd like to better forecast is conditions that create icing on ships. And so here's a lovely photo of icing along a ship railing out in the North Atlantic. And you can see that this would clearly be a very dangerous situation for anyone on the ship. The ice weighs quite a lot. It creates for a very dangerous working environment. Here's another picture of conditions on a research vessel out in the North Atlantic in very dangerous icing conditions. Again, you would not be wanting to walk on this deck. Another situation that, again, all of these have end users in mind. So in particular, any ships that do research or fishing vessels or anything of that nature, but extreme wave conditions. They really want to know when are these events going to happen, how to correct their voyage journey to maybe avoid such events. So extreme waves. Here's a lovely photo of waves crashing over the deck of a research vessel. Again, the sort of situation where you would not want to go out if your vessel is not capable of handling situations like this. And then lastly, another one, quite severe waves. You can see the CTD rosette there on the corner, all strapped down. So situations where it's really unsafe if your vessel, again, is not capable of handling this. So in addition to icing and waves, we're also really interested in being able to better forecast polar lows. And so these are very small, very relatively small low pressure systems formed in the Arctic, primarily during the winter time. They move very rapidly. They develop very quickly. They have very strong winds, very high waves. And again, because their development is highly dependent upon the air-sea temperature difference, being able to have a coupled forecast model would hopefully improve the prediction of these such events. On the right, you can see a couple metrics of our skill with forecasting these events. And so we're looking at the bias and the mean absolute error of mean sea level pressure, as well as the 10-meter winds, as a function of distance from the center of the low pressure. And so you can see that the errors increase quite rapidly as you get very close to these low pressure systems. And so being able to better predict what is happening around the center of these low pressure systems is really one of the goals of this project. Another one is to better simulate or better predict what is going on with the wave ice interaction. So this is a video taken by one of my coworkers. They were deploying wave measurement buoys out in the ice zone near Svalbard. And he took this video as they were exiting the marginal ice zone. So you can see the waves propagating into the marginal ice zone and being able to forecast how these waves and the marginal ice zone interact is really important. In this situation, the waves damp very clearly, or at least the high frequency waves damp very clearly. But if the ice perhaps is thicker than this, we'd really want to be able to forecast what is going on. Perhaps that are simulating ice breaking events. The ice here is very small, but if the flows are of much larger size, being able to simulate their breaking could be quite interesting as well. And so really the dream here is developing a fully coupled forecasting system that has an atmosphere, which we already have. So we've got our fully dynamic atmosphere system, coupled to a sea ice and snow model, coupled to a wave model, coupled to an ocean model. This would be very expensive to run in a forecasting sense. We're running 66-hour forecasts every 12 hours. And so running this on a 2-kilometer resolution over our domain would add up very quickly. But as computing power improves, we're slowly getting there. But the reality for now is that we have our atmosphere, a very simple sea ice model, coupled to a wave model. And so the atmosphere model that I'm using is called Arome Arctic. You saw the domain in a previous figure, it was highlighted in blue. And so that's the region that this model focuses on. We have very simple sea ice and snow representation within this model. It's a one-dimensional thermodynamic model for ice. And so we have daily varying ice concentration and ice thickness. But it's not reacting in any way. It's static for the day, feeding in from satellite data and ECMWF. The wave model that I have spent 2 years coupling this system to is called WaveWatch 3. And so interestingly, it takes one slide to show you 2 years of work and several slides to show you roughly 1 year or 1 month of work. And so the distribution of this presentation is quite lopsided in terms of the effort. But the basic coupling strategy that we're using is through momentum coupling. And so we are passing the 10-meter winds as well as the ice fraction and ice thickness information from our atmospheric and ice system to WaveWatch, which calculates the full 2-dimensional wave field. From WaveWatch, we get a surface roughness parameter, and that is the variable that's passed back to the atmosphere to close the momentum coupling loop. So a fairly simple momentum coupling design to allow the ice, simple ice, the atmosphere, and the waves to all interact. All of the coupling is done through a third, sorry, I think I see a hand back there.
Yeah, I have a question, Erin.
Sure.
Sorry.
Yeah.
Very interesting. Does the atmosphere on top know that the surface area of the underlying ocean is effectively increased under certain wave conditions and thereby enhances, evaporation and heat transfer?
Yes, absolutely. So those are all secondary, but we're not directly modifying any of those variables, but through the change in the surface roughness, we're changing wind speed. And so we're getting changes in evaporative fluxes and that kind of thing as well. Yeah, but those are all secondary effects. We're not going in and directly modifying any of the fluxes. All we're doing really is changing the surface roughness, and through altering the winds, we're getting secondary effects on all the heat and precipitation and moisture flux. That's what I was looking for. Yeah.
Okay.
Just another quick question. So the coupling of surface roughness back to the atmosphere comes through the wave module. How big of an effect is ice like for larger flows, or does that, how big of an effect is that on surface roughness? And is that taken into account?
So no, our representation of ice here is pretty coarse and very smooth. And so we're getting some effect of damping of the waves into the marginal ice zone. It doesn't have a huge effect on the roughness. And so the atmosphere, it essentially is seeing a tiled surface. So the 2.5 kilometer grid resolution is broken down further into individual tiles. It's like a subcategory of the grid cell. And so it is seeing sort of a sub-grid scale representation of maybe what is ice and what is ocean or what is land. But yeah, we're not seeing a huge impact. I mean, the wave damping into the marginal ice zone happens on such a small scale versus the region that we're simulating over that it's not huge.
Got it.
If I understood your question correctly. Yeah. And so, yeah, the surface roughness over open ocean is changing quite a lot because we're adding waves. But then, yeah, once there's ice coverage, it's, I mean, the atmosphere is really only seeing ice. So just another representation of what's going on here. Again, we have our 10-meter winds, ice passed from our atmosphere to the wave model. The wave model then calculates the wave field, so a total and wave-induced stress. These variables go into calculating the Charnot parameter, and this is actually the value that we pass back to the atmosphere. And so the atmosphere itself calculates what the surface roughness is from the Charnot parameter of the full wave field. And then, as I previously mentioned, this goes into the drag coefficient. And so we're not only modifying winds, but we're getting secondary effects on moisture as well. So those slides took, about 2 years worth of work, but I'll talk about once the development was done, the experiments that I ran with this to verify how well the model is performing. And so I ran 2 experiments. One was fully coupled and one was uncoupled. I was initializing 48-hour forecasts every 12 hours. And I ran this simulation, or both of these simulations, for roughly 1 month of time during December, January. So in the uncoupled simulation, I have the atmospheric variables forcing the wave model, but there's no feedback mechanism. So the wave model simulates the full wave field, but the atmosphere is essentially unaltered by anything that the wave model is doing. In the fully coupled simulation, as I showed on the previous slide, we have the Charnot parameter being passed from the waves to the atmosphere, and then the wind and ice variables being passed from the atmosphere back to the wave model. The way that the coupler works, in order to prevent a deadlock in the system, so information trying to be passed 2 ways, we did have to introduce a time lag in the Charnot parameter. So the information from the wave model is actually coming from the previous time step, getting passed to the wave or to the atmosphere model at the present time step. And so this just avoids, because there's a dependency on these variables, it avoids a deadlock in the system where information is trying to be passed 2 ways. Just a few more details. The atmosphere runs with a time step of 1 minute. Again, the spatial resolution of both of these models is set up to have 2.5 kilometer resolution. And so we're running a pretty high resolution system here. So 1 minute temporal resolution in the atmosphere. The wave model is set to have a time step of 5 minutes. And the coupling frequency, so the frequency in which the models are exchanging information, is set to 30 minutes.
That wave lag that you had there, that's the lag in terms of the feedback to the what's the parameter that you're talking about?
The Charnot parameter?
Yeah.
Yeah. And so at the very first time step, we initialize that as a static variable from an external field. But all throughout the rest of the simulations, the Charnot parameter from 5 minutes ago gets passed to the atmosphere now. Does that make sense? Right. So, I'll briefly present a few results here. So the first thing I wanted to do was make sure that including a wave model to our atmosphere forecast actually did what we expected it to do. And so in theory, we are adding waves to a previously smooth boundary condition. And so I would expect the surface roughness to increase, which it does by quite a lot. And so that's really good. We are getting an effect from the surface roughness to the atmosphere. So we see an increase in the surface roughness. Because our surface roughness is increasing, we see a corresponding decrease in the 10-meter wind speed. And with a decrease in the average wind speed, we are also seeing a decrease in the average significant wave height. And so here we're just looking at anomalies, the fully coupled model result minus the uncoupled models, right? Just the straight mean across the full 1 month experimental time period. And so nice little sanity check that adding in waves to a previously uncoupled system does in fact do what we expected it to do. But more importantly, we want to look at, well, how is the forecast? And so we performed quite a few validation runs against satellite-based observations, and I'll just highlight a few of the results. So here, hold on a second. I'm trying to like move my face around, but let me see if I can get rid of.
know if what I do here affects her though.
No, here, I just hid, it was like showing me a sidebar of like all of us, and it's just distracting because it blocks some of the slides. So it's all fixed now. So we ran a couple of validation experiments against satellite-based observations. So on the right-hand side, we're looking at the significant wave height. And on the left, we're looking at the 10-meter wind speed. On the y-axis, we're looking at the values from satellite-based observations. So for wind speed, we're using ASCAT data. And then for the significant wave height, we're looking at satellite-based altimetry data. And then the x-axis for both of these figures is the wind speed or significant wave height from the coupled model. And you can see that there's very good agreement in the coupled model versus what we observe from satellites. Although that there's a much larger spread for the wind speed variables as opposed to the significant wave height, which does seem to have a much tighter fit around that diagonal one-to-one line, which would be a perfect fit. Just a few more details. These are all co-located data for the fully coupled forecasts at lead time of 0 hours. Remember, I was running 48-hour forecasts at 12-hour intervals. So I can repeat the same analysis, not only for the fully coupled simulations, but also the uncoupled simulations to look at the difference of what actually coupling to a wave model does. Not only for the forecast at lead time 0, but at all forecast lead times. And we can look at these results as a function of lead time. And so that's what we're looking at here. So again, 10-meter wind speed variables are on the left. The significant wave height is on the right. We're looking at the standard deviation of the errors, as well as the correlation of the fit. So the fully coupled model results are in blue and the uncoupled model results are in red. And what we're seeing is there is a decrease for both the 10-meter wind speed and the significant wave height in the standard deviation of the error, meaning that there's actually a tighter fit, that spread is less for both of the variables. We're not seeing a very strong indication or a very strong change due to the coupling in the correlation of the wind speed. However, we are seeing a slight increase in the correlation in the significant wave height variables, meaning that the coupling actually improves the correlation with satellite-based observations, as well as produces a tighter fit around the satellite-based observations, or a stronger fit, less error, less spread. So another way that we can look at this is breaking it down by category. So the previous figures, we were looking at the results as a function of lead time for all wind speed and all significant wave height values. However, it's really interesting to break this down in terms of binned wind speed and binned significant wave heights. So do we see more influence of the coupling at different wind speed and wave height values? And so we're looking at the mean absolute error in this case, as well as the error standard deviation again. And we see the biggest improvement due to coupling at the highest wind speeds and the highest wave heights. So for 15 to 20 meter wind speed and 20 to 25 meter wind speed, we are seeing the biggest decrease in both the mean absolute error, as well as the error standard deviation at these two highest wind speed categories. Similarly, we see the biggest decrease in, again, the mean absolute error and the error standard deviation at the two biggest categories of the significant wave height. So 6 to 9 meters and then waves over 9 meters. And then lastly, we were interested in comparing our forecast results with land-based station observations as opposed to satellite-based observations. And so I selected 3 of our stations that are very coastal, which will have the largest effect due to wave coupling. Most of the stations that are further inland have very little impact due to the wave coupling. And so I focused on very coastal marine-based stations. So I picked 3 stations as an example. They're on the left. So there's a red, a blue, and a green station. And we're looking at the comparison of the observations from the land-based station, as well as the fully coupled model and uncoupled model. And so we're looking at the station surface pressure as well as the wind speed. The solid lines show you the observations. The dotted lines are the uncoupled model, and then the thick dashed lines are the fully coupled model. There's very little influence in our sea level pressure forecasts. However, if we zoom into a few events with the wind speeds, we can see some very interesting results due to the coupling. So if we focus on the green station, for instance, we actually see an overall improvement at all time steps for this few day period that we're looking at here. So the fully coupled model is actually outperforming the uncoupled model at this station over the full four-day time period. And additionally, the other 2 stations are also showing some interesting results. The fully coupled model is capturing some of the more extreme events. But again, this is really just 4 days worth of study. Overall, it's suggesting quite promising results that we're capturing, particularly at Bjørnøya, which is the green station here, that the fully coupled model is consistently outperforming the uncoupled model. But really, these sorts of case studies don't tell us too much, and we really need to have more testing. And so this fully coupled atmosphere wave system is currently in our pre-operational setup, where we'll be able to run daily forecasts and test throughout the year in many different kinds of situations, whether or not our model is performing well. And so that is our current status. Again, we have our atmosphere model coupled to a simple non-dynamic sea ice model coupled to WaveWatch 3. But we're doing a whole lot of different stuff. And unfortunately, there's no results coming out of our ongoing work, but we are working on improving our sea ice and snow representation. So we are updating our simple non-dynamic sea ice model to a fully dynamic ice model. We're going to be using size 6. And so we actually have this 3-way coupled system in place. It is technically working, but the interactions between ice and waves are not very well known. And so tuning a system like this is quite a challenging undertaking. And so that is one area of very active research here at Met Norway. And so the video I showed you earlier, as my coworker was exiting the marginal ice zone, what they were doing out there was deploying sensors on ice flows that are measuring the waves underneath the ice. So as the ice flow is bobbing along in the waves, the sensors on top are measuring the spectrum of the wave field below it. And so our idea is to use these floating wave sensors to further validate the ice wave atmosphere fully coupled system that we're running. We're particularly interested in being able to capture the wave attenuation into the marginal ice zone correctly, as well as capture the ice edge movement and ice breaking events near the edge of the ice zone. And so hopefully we'll be able to use these wave sensors that are out in the Arctic floating around on these ice flows. But again, this is just our idea to help us tune our currently technically working model. But again, yeah, tuning this system is quite challenging, and there's not enough observations. So the few observations that we have, we're hoping to be able to utilize to help us tune the model better. Additionally, one of the other challenges in terms of adding sea ice, especially with the ice representation that we currently have in the model, is that, well, the ice representation we have is very smooth and does not capture any high resolution features in the ice. So in reality, the sea ice, it has quite a few small scale ice features, such as sea ice leads. And it turns out that these small scale features have very large impacts on the heat and momentum flux to the atmosphere. So being able to resolve features like this has very strong local and non-local impacts on the atmospheric forecast. And so the top figures here shows a typical example of the sea ice representation in our current setup. You can see that the ice edge is very smooth and doesn't represent any of these ice leads or small scale sea ice fractures. So in the middle, we're looking at sea ice from MODIS, and then on the bottom, we're looking at the sea ice images from SAR. And you can see in both of these cases that the actual ice in reality has cracks. There's regions of open ocean, and none of these features are currently captured in our model. So hopefully by including a dynamic sea ice model such as SICE, we could better resolve some of these features. The other thing that we're really interested in capturing is upper ocean temperature variability. And so rather than focusing initially on a full three-dimensional ocean model such as ROMS, we're messing around with including a one-dimensional ocean turbulence model instead. So one that is capable of having reactive sea surface temperatures to some of these severe weather events. So when a cold air outbreak happens, the fluxes that occur between the atmosphere and the ocean can be quite important and change quite rapidly. And so we're hoping that having reactive sea surface temperatures in situations like this can also help improve our forecasts. But again, moving to a full three-dimensional ocean is a little bit overkill when we're talking about 48-hour to 66-hour forecasts. So we're hoping that maybe a one-dimensional ocean turbulence model will be able to capture this sea surface temperature variability without being excessively costly to run. So one of the problems that we're having with this, again, especially with this three-dimensional ocean model, or at least the operational ocean model that we run here at Met Norway, is we have very large sea surface temperature biases in this model. On the left, we're looking at the OSTIA satellite product of sea surface temperature and the turbulent heat flux. So this is currently what is represented as our boundary conditions. And then on the right, we're looking at the results from MET-ROMS, which is our current operational three-dimensional ocean model. And you can see, for instance, that the Spitsbergen current that flows up close to Svalbard is much stronger and has very large sea surface temperature biases in this region. And unfortunately, this is really important because this is a region that's often covered by sea ice. And if our sea surface temperature biases, which are in excess of 4, 5, 6 degrees sometimes, it melts all of our sea ice. And so it actually degrades our forecast. So we're hoping that maybe a one-dimensional ocean turbulence model can alleviate some of these biases as an intermediate step while we improve our operational ocean model. And so this is my last slide. So in conclusion, our atmosphere wave coupled forecasting system looks very promising as of right now, but there is so much more to be done, not only to our current atmosphere wave system, but also towards developing a fully coupled Arctic forecasting system where we have better representation of ice and the ocean surface. And a special thanks to my mom, who provided all the fun photos of extreme weather at sea from some of her research cruises in the North Atlantic and Gulf of Maine. And so, yeah, with that, thanks.
Thanks. Let's see. Back to the view of everybody.
Right.
All right.
Steph's got her hand up. Go ahead, Steph.
Hey, Erin.
Hey,
It's
Steph.
really good to see you, and it's really cool to hear about what you're doing. This is awesome. So I have a question that you may not know the answer to, So it may turn into more of a comment. But one of the things I work with a lot is blocking in this region. And sometimes we see that when we get a block that sits up kind of over Iceland,
Mhm.
and it essentially blocks the mean westerly flow over Northern Europe. And you get storm systems, that cyclones will get rerouted essentially towards your region,
Yeah.
in the blue square. I'm curious, I mean, given that this is a region that is often impacted by things like blocking, I'm really curious as to how, if your model would handle certain situations.
Yeah, and so the example that I was showing with the 3 land stations that I was comparing against, I particularly picked that like 4 or 5 day window to focus on is because we actually had one of these low pressure systems propagating up through our southern domain. If I can like go back there real quick. Here. You can see I mean, I didn't show the satellite images of this system propagating up through just to save on space and time, but you can see the signal of the low pressure system of the land station. So like it's propagating through the blue station first, and then you can also see the signal as it goes between sort of Bjørnøya and Lofoten later in time. And so, yeah, I did actually pick one of these situations to focus on to see how well it captures some sort of storm. Unfortunately, there was no polar low to look at. And so one of these sort of more southerly low pressure systems was the next best thing. But you can see the signal and the wind speed as that storm hits Lofoten. We're actually capturing the onset of that increase in wind speed a little bit better in our fully coupled systems. So that's the dashed line. Granted, again, we're only getting some like minor improvements. I wouldn't definitely would not say anything conclusive from this, but the fully coupled system does seem to be able to capture some of these events pretty well.
That's pretty cool. Thanks, Erin.
Yeah. There's some hands in the room too.
Go ahead, John.
I'm curious about this same result, Erin. It's kind of interesting. One might imagine that if you are dealing better with the momentum transfer and the boundary limit or the friction limit, and slowing the wind speed down as a consequence, I think is what most of the results seem to show, that you showed today anyway, that you might have less accumulation of mass in the boundary layer by cross isobar flow, and the pressures might not get quite as low in your coupled model as they do in the uncoupled. And that goes a little bit all over the map. It's not always consistently the case. Do you have any comment on that?
No, not without further testing, I think. The difference between the fully coupled model and the uncoupled model, especially in terms of our sea level pressure, is nearly identical. As you can see here, you can't differentiate the coupled and uncoupled model when we're looking at the sea level pressure forecast.
Yeah, that's what rather surprises me, but it might be because the forecast of the sea level pressure, regardless of which model you use, has something to say about the wind speed, which has something to say about the mass accumulation in the friction layer and so on. And so
Yeah.
they're kind of looped together a little bit, tied together a little bit. Anyway, it's interesting that that's the case. I think what you're doing is great. I think you're really starting to gain some refined insight on what goes on in that icy boundary layer, which is great.
Yeah, and I think, like I said, I mean, this was just our very initial study, but we're putting this in our pre-operational system. So we're not replacing our operational system, but testing all of our current developments in sort of a quasi-operational setup, so we can better look at some of these results. I mean, 1 month time period is not nearly enough to get a good, robust analysis of how this system is performing. And overall, the effect of the waves on the full forecast is very small. And unfortunately, we didn't have any of these more severe situations to look at, any more severe sort of case studies. And so hopefully we'll be able to capture some of these more severe events. And we do expect the biggest results again to be when we're having the most severe weather. So the highest wind, highest wave sort of situations. So it'll be interesting to see what comes out of the pre-operational results during some of these more severe cases. So this winter is going to be great.
See, you always should look forward to winter. I agree with you.
Yeah, the best weather happens during winter. Yeah.
Yep.
So if you didn't capture any of the polar lows then?
No, unfortunately not. I mean, we ran out of computing time, so it's a very expensive system to run. And so I had to cut off the experiment because I was running 2 simulations, right? Not just the coupled simulation, but the uncoupled one as well, to look at exactly what's going on due to the coupling. And yeah, we had to chop it off after 1 month. And so unfortunately, right after we ended the simulation, like 2 weeks later, we were actually getting some of these polar low events in the domain. But yeah, it was computationally too expensive to keep it going. So.
Hi, Erin.
Hey.
I have a question. Do you know how those wave sensors on the ice flows work, or is it just a GPS or what?
So there is a GPS, but it's a motion sensor. And so I'm not 100% sure. A PhD student at the University of Oslo developed them as part of his PhD. And so the GPS gives back the location, obviously, but there's a motion sensor, and I'm pretty sure it's the motion sensor. And somehow it's able to capture the full 2-dimensional spectra of the wave field below the ice flow and categorizes it. So yeah, these wave sensors are awesome. Unfortunately, we only have a few of them out there, but I ran one experiment the same time frame as this when there was a couple wave sensors out there, and we're capturing pretty good wave attenuation into the marginal ice zone. But yeah, no, I'm not sure on the details, but there's a motion sensor and somehow it's able to give us the wave field. And
Okay, thank you.
I can give you the paper that talks about it if you're interested, Karen.
Sure.
Sure, yeah.
Do you have a sense for, sorry, I'm jumping in here. Do you have a sense for for future work, what's gonna make the biggest improvement? Changes in the sea ice module itself, or coupling with turbulence, or are we unconstrained enough by actual observations that it's just sort of a crapshoot whether that's going to help or not?
So I think that the biggest improvements do seem to come from our previous developments in the sea ice model. And that seems to have large jumps. Whether or not we get drastically better improvements by going from our fairly simple representation of sea ice to a full ice model, I'm not sure. Because we do have estimations of ice concentration as well as the ice thickness, and really to capture sort of wave attenuation into these fields. That's all we need. And so whether or not we're actually representing individual ice flows and their breaking, while scientifically I'm totally interested in that, whether that has huge improvements on our actual forecast, I'm not sure. I do think we could get some interesting results from including a reactive sea surface temperature, but again, I think we're talking about fairly minor improvements to the atmospheric forecast at this point. Just as computational power goes up and stuff, we are getting more adventurous with what we're including. But also this model is fairly highly tuned to this region. And so all of these things that we're adding in actually further complicate the model. And some of these developments and improvements degrade our forecasts actually. And so creating significant improvements in a forecast at this point is really hard. Our goal is to not make the model worse actually.
But I think, what you showed is that the biggest improvement you're getting is in the forecast of the wave heights and the extreme wave,
Yes.
extreme wave zone.
Yeah.
That's the fact that you can incorporate like your last comment there, I think is an important one to sort of take to heart, right? I mean, the fact that you are able to get improvements in that while not breaking the model is pretty impressive.
Yeah. Yeah, and particularly to forecast icing events, having a fully coupled wave atmosphere system where the two models are essentially simulating the same situation, I think we could greatly improve the regions of our icing forecasts. And so reduce the uncertainty on where they're occurring, when they're occurring, and things like that. And so we've got several people in Tromsø who are working on icing forecasts. And I know that they're the ones who are most interested in getting their hands on this fully coupled system. And so, yeah, there's definitely some areas that are greatly going to improve, I think, from a coupled system like this. So, yeah, so kind of cool.
So, and then I guess a follow on to that, I mean, your next task, I suppose, at Los Alamos is going to be incorporating this into E3SM.
Yeah, so E3SM, I'm not like fully sure what sort of projects I'll be working on when I get there, but it's kind of still under development. And so their goal is to really improve the coupling in the Arctic. And so I'll be working with, I think, primarily waves and ice, but yeah, those details aren't ironed out yet. So it'll be interesting to see what I'm working on. But yeah, all Arctic forecasting, Arctic, it's a climate model. So I'll have to readjust my framework here.
Yeah, but that's, I mean, I guess that's my question is, what do you see as the biggest, the biggest challenges or the differences between this forecasting framework, which, you've been working on for the last few years compared to climate? What are the biggest?
Yeah. I think that's a really good question. I mean, so this forecasting system is super constrained on the boundary conditions and super constrained on data assimilation, and none of that exists in the climate model. And so I think a sea ice model is going to be much more important in a climate model like E3SM. I think the ocean representation is also going to be way more important in a climate model like, well, any climate model for that instance. I mean, when you're talking about 66-hour forecasts, these conditions have, especially the ocean, it doesn't change rapidly. And so our forecasts with static sea surface temperature are super accurate. And so if we include sea surface temperature variability, like, are we actually going to be making any huge improvements? In a forecast, maybe not. In a climate model, yeah, absolutely. And so I think the coupling in a climate model is actually more critical than coupling in a forecast system.
Yeah, and given I think some of the results from US5R's look at high latitude fluxes showing that snow on ice and representation of broken sea ice and so forth in terms of changing the surface fluxes at higher latitudes is the biggest uncertainty, and there are enormous consequences of those things. So yeah, I mean, even in our forecast system, one of my coworkers focuses much more on the sea ice stuff, and all he did was add representation of a snow layer on top of the sea ice, and we got huge improvements in the forecasts just because we've all of a sudden changed the thermodynamics at that boundary. And so you're getting that insulating effect, and our skill in the Arctic forecasts went way up. And so I think it'll be quite interesting. But these kinds of features can have huge impacts depending on.
That storm tracks delivering ice on the snow on the ice are really critical even in climate models. Oh yeah, so if you don't get the storms right, how are you going to get that right?
Yeah, absolutely. Yeah. So even the systems that are important in climate, some of them are important in both kinds of systems. So absolutely.
I think you're getting a great person in you, Erin, because you're going to this coupling problem on, as you say, for this kind of a time scale and this kind of a problem. That
these are minor improvements in a coupled model. They're going to be critical to get correct.
Right, and you've got the right mindset to see that. But hopefully, you'll also have the mindset to remind them that storms matter. And the climate model doesn't know what it's doing with storms. It's got no chance of doing anything else right.
Absolutely. Yeah.
Everything looks like a nail to the guy with the hammer.
Vice versa.
That's right.
Erin?
But he's right.
In one of your early slides, you showed the difference between Southern Norway and Svalbard as far as differences between what the predicted values were and what the actual values were. Do you think that's more as a as a result of modeling, or is it the direct effect of climate change?
This figure here you're
Yes,
referring to?
yes,
Yeah, no, I think this is just the modeling. I think this is our ability to forecast what is going on at these regions. Again, our skill is pretty good at southern latitudes. That's where our greatest density of observations comes in. And so we have data assimilation going on every 3 hours in this system. And so where our observations are very thin, also, we're getting our pretty good boundary conditions from the high-res ECMWF model. And so I'm reasonably confident that the boundary conditions are good. And so I think a lot of this is the skill of our forecast model at this point.
No further questions. Then let's thank Erin once again.